We're going to look now at the classification of critical points. But before we get there, let's talk about local and global extrema. So if a function f is defined, let's say, for two variables, and it's the same for more variables, is defined on D, then we say that f has a maximum at AB if the output at AB is greater than or equal to any other output in D. But if the function happens to have a point where the output at that point is larger than all neighboring outputs, not all outputs in D, but just neighboring output, let's say the outputs on a disk surrounding that point, then we say that we have a local maximum. So if AB is a point at which f of AB is greater than f of xy for every xy in a disk surrounding AB and presumably in D, then we say that f has a local maximum. The picture actually here can be made much simpler by looking at the corresponding notion for functions of one variable. So if you have a function of one variable, take a look at this picture. Let's say that this is the complete graph of the function. Then you can see that the maximum of the function is at this point right here. But then these 2 points are also points that are where the output is the largest possible in a small portion of the graph of the function on an interval surrounding that point. So these two are local maxima, and this is a global maximum, or the global maximum, because there doesn't seem to be another one. But let's note here that a function can have global maximum and local maxima. A global maximum is automatically also a local maximum, and there's no particular need for a function to have any of those things, or you can have a function that has just local maxima and has no global maximum. So in some sense, everything is possible, with the exception that if a function has a global maximum, then obviously it will have a local maximum. Now, we're going to see in a second why it's important to consider local maxima. But before we do so, let me just state the obvious here, that we can have the corresponding notions with minimum. And of course, the inequalities will have to be reversed. That is, the output at that minimum will have to be the smallest either from any other output if it is a global minimum, or from the outputs in a disk surrounding the point if it's a local minimum. And the inequality is reversed. And we can actually use one word to describe both minima and maxima, and that's the word extrema. So extremo is minimum or maximum. For constant functions, it will be both. And let's just also finish this little journey in terminology by just saying that for the global maxima, we can actually use also the term absolute maximum. Or just maximum. In some sense, global and absolute is an emphasis on the fact that it covers the whole domain of definition. Whereas for local, there's also the term relative, which can be used in an equivalent way. Okay, so now let's see, philosophically speaking, why do we need local extrema? So what we really want to know in most cases is whether a function has a global maximum or a global minimum. But the points that are easier to detect are the local maximum and the local minimum if they happen to exist. In fact, it turns out that if a function, again, let me state this for two variables, but it's true for more variables. If f of xy has a local extremum at AP, and AP happens to be in the center of a disk, and AB is an interior point, of the domain of definition. Then the gradient of f at AB has to be equal to 0. And actually understanding this is not such a hard thing because you can take any path that goes through your local extremum, then the restriction of the function on that path will also have a local extremum as a function of one variable. And so the derivative in that direction will have to be 0, meaning any directional derivative would have to be 0. And the only way that a nice function can have all directional derivatives being equal to 0 is if the gradient is equal to 0. And but here comes the problem now. I mean, it seems so far that we have an ideal situation, but it's not true. It's not true that the condition that the gradient is equal to 0, and 0 here should have been marked with a vector, of course, implies that AB is a local extremum. And here one can give very, very simple examples. So, for example, take the function f of xy to be x cubed plus y cubed. I could have taken it just to be x cubed. Allow me to do this. Then obviously the gradient of the function at 0 is 0, 0. But exactly because the degrees of the variables x and y are odd, that means that if you move a little away from 0, 0 in a well-chosen direction. So for example, if you move along the positive x-axis, you will get outputs greater than 0. If you move onto the negative x-axis, you will get outputs that are less than 0. And your function certainly doesn't have any kind of local extremum at that point, even though the gradient is equal to 0. What will happen geometrically is that its graph is going to be a little flat, and it's actually much easier to visualize it for functions of one variable. I'm not going to try to do anything with any kind of graph visualization here. But the best graphs you can find should be computer generated in this context. But what should be noted is that in some sense, there are more critical points than there are local extrema. So when you have a critical point, you don't know if it's a local extremum. However, it's a good start. It's a good start. So, so we have a plan. You want to find global extrema, start by finding local extrema. How do you find local extrema? Find the critical points and try to see if you have a local extremum at those points. And we would like now to see what kind of situations we can have, at least for good functions. So the question is, what can go wrong? So what is going to happen in a case like this, for example, and an extremum might not occur? Basically, what will happen in general is you will be able to find one direction. Actually, what I'm going to say here is not true for this particular function, but this is a way that this can work. So you can find one direction, and that's why I'm drawing only a curve here, along which the function has a minimum, and another direction along which the function has a maximum. And basically, you have a configuration, at least as far as a surface is concerned, that looks like a saddle. If you imagine how a saddle looks like, then you will have exactly that kind of situation. So if you think of the surface of the saddle, then and you think at the point where the rider touches the saddle, then the you can have one direction along which you can visualize a local minimum, and another direction along which you can visualize a local maximum. I like a sort of example that has been brought forward by Terence Tao, pretty much the most famous mathematician of contemporary mathematician, who has said that, well, instead of looking at a saddle, you can look at a Pringle. The Pringle is an object, I'm sure we have all eaten Pringles. The Pringle is an object where you will have two directions, one that gives you a local maximum, another that gives you um, a, a maximum, another that gives you a minimum. And at the end of the day, there is no extremum at that point. That's why we will try to do a classification of critical points. And we eventually want our classification to have one of the three conclusions for each point. It will be either a local maximum or a local minimum or a saddle point. Allow me here to put in a parenthesis, Pringle point. Again, it seems that we're doing a free commercial for Pringles, but then again, this is a math lesson after all, so who cares? I don't see the Pringle company using this concept anytime soon in order to promote their products. But anyhow, we have a very nice theorem that tells us which is which. As usual, expected with those theorems, they work most often, but they don't work always. And you will see what I mean in a second. So here comes our theory, our classification theory. Suppose that AB is a critical point in the interior. When I say interior here, I just mean that the point is surrounded by an open disk or is inside an open disk where the function is defined. Of the domain of definition of a function f of xy. We define a discriminant, a determinant D that consists of second order partial derivatives. So we put f sub xx a b here, f sub xy at a b here, then f sub xy at a b. You could have put fyx, but by Clairaut's theorem, they're the same for all the functions that will be of interest to us. And I remind you how this determinant works, of course. This would be fxx at ab times fyy at ab minus fxy at ab squared. And here are the conclusions. Then, if d is less than 0, AB is a saddle point. If D is greater than 0, then f of xy has a local extremum at AB. More specifically, in this case, in other words, if fxx at AB is positive, think about your knowledge of functions of a one variable. If you have a second derivative positive, then that means that the function is concave up. Concave up is exactly the shape of a smile, which is the shape of a local minimum. So more specifically, if f sub xx of AB is greater than 0, then AB is a local minimum. And if fxx at AB is less than 0, then AB is a local maximum. There are a couple of things to note here. So one would ask right away, in this case, in the case that d is greater than 0, what happens if fxx at AB is 0? And this can never happen. Okay, this simply can never happen, because if fxx at AB was 0, then this quantity would be 0, and then your determinant would simply be minus the square of some number, and this can never be positive. You could never have that it's greater than 0. Okay. There's another remark that needs to be made here, and the remark is that notice that we don't say anything about the case that d is equal to 0. If d is equal to 0, then this test is pretty much useless. Sometimes you will see that it's included in the statement that if d is equal to 0, then the test is inconclusive. But I'd rather not do that, because sometimes people get misled and they actually write as their final conclusion that, okay, the test is inconclusive. The story doesn't finish there. It doesn't end there if if d is equal to 0. If d is equal to 0, you have to do something else in order to find out what is going on. That, for example, would have been the case with this function right here. If you try to apply this, which is going to be known as the second derivative test, sometimes people might even call it the second partial derivative test. I will just call it the second derivative test, because if you apply it to functions of several variables, then it's obvious that you're going to be considering partial derivatives. So for the function that I just gave you, this test is going to be inconclusive. It's going to be useless. And you will have to use, for example, a remark like the one that I made in order to conclude what is going to happen. There are many, many interesting things that can happen when the test is inconclusive, actually. But to be honest, in pretty much all the cases that will be of interest for us in this course, the test will be conclusive. So we will be able to know after we apply the test whether there is a local extremum or not. Now, this is one of the rare cases in our multivariable calculus course where we have to say that the generalization to higher dimensions is not obvious. It's not something that you can just do routinely by just looking at this statement and say, oh, okay, in 3 dimensions, it's going to be like this. I mean, you might actually try to take the discriminant, I'm sorry, I keep saying discriminant, the determinant of a similar 3 by 3 matrix. It's just not true that you can draw the same conclusions. In fact, There is a direct generalization for all dimensions, but it's much more convoluted, and it depends on a criterion by Sylvester for matrices being, as we say, definite, either positive definite or negative definite. So interestingly enough, we're going to really stick to two dimensions when it comes down to classifying critical points. Okay, I think we have everything on the table that we would like to have, and it's time to give some examples. So let's start with our first example. So we're going to say find and classify the critical points of the function f of xy equals to x cubed plus y cubed minus 3xy. Okay, so the very first step consists in finding the critical points first. And how are we supposed to find the critical points? So we will take the derivatives of the function. Here they are. And we will set them equal to 0. We will set them equal to 0, and we will get a system. And usually the systems that you're going to get in this business are going to be nonlinear, and there are no general methods for solving such systems. But one thing that you could try is try to isolate one variable in one equation and plug it into the other in the hope of getting one equation with one unknown that can be solved. And actually, this hope materializes here. We can exactly do that. So first of all, let's see, we can slightly simplify the system by dividing through by 3. So we can have x squared minus y is equal to 0, and y squared minus x is equal to 0. And if we take the first equation, we can write y is equal to x squared, right? So now, what did we say? We said that you could take this, the x squared, and plug it where you see y, right here. And if you do so, then the second equation is going to yield what? X squared squared minus x is equal to 0. And all of a sudden, we obtained an equation that has just one variable. And let's see if we can solve this. X to the fourth minus x is equal to 0, which gives us x times x cubed minus 1 is equal to 0. And this can be further factorized as x times x minus 1 times x squared plus x plus 1 being equal to 0. And obviously, this is never 0 right here. This is never 0. So by using the first two terms, we find that either x is 0 or x is equal to 1. And now we just go back to our equation that gives us the relation between y and x. And we see that if x is 0, then automatically y is 0. And if x is 1, then y is 1, which means that we have two critical points. We have found two critical points, 0, 0, and 1, 1. These are all the critical points of this function. And now it's time to classify them. Okay, so let's classify these critical points. How do we do this? Let's start with 0, 0. And actually, I should find the second order partial derivative. So what is f sub xx? Because I will need them in general. It's 6x. What is f sub yy? It's 6y. And what is fxy? It's just a constant -3. Okay, so if we take the determinant for this specific point, so at 0, 0, fxy at 0, 0, fxy at 0, 0, and fyy at 0, 0, what do we find? We find 6 times 0, which is 0 right here. then the next entry will be simply -3. This will be -3, and this will be again 0. That's what you get if you plug in 0, 0 into the second order partial derivatives. And this gives you just -9, which is less than 0, so this is a saddle point. So 0, 0 is a saddle point. Okay, let's see what happens with 1, 1. So I will take D to be fxx at 1, 1, xy at 1, 1, fxy at 1, 1, and fyy at 1, 1. And this will give us what? 6. Again, -3. Those do not change since the fxy was constant, and another 6 here, which will give actually 36 minus 9, that's 27, which is positive. So we do have a local extremum right here. And what kind of local extremum? Well, take a look at the second derivative with respect to x to i's. It's positive. It's positive, which means that this has to be a local minimum. And that completes the classification of critical points for this particular function. It might be a good idea to do one more example, but let me, before I proceed with the next example, let me just say a little, what is the essence of this theorem? So what do you achieve here by knowing that this specific determinant is greater than 0? The determinant being greater than 0 eventually tells you that you will have the same behavior, meaning for in terms of concavity, if you like, in all directions. And that is what forces eventually the presence of a local extremum. The part that determines that is pretty much the second order part of a Taylor expansion. So it's a Taylor polynomial, and it turns out that that polynomial has as discriminant, it's a second degree polynomial, exactly this determinant. In the case that d is less than 0, what that implies is that pretty much you're not going to have the same behavior in all directions. In fact, you will have directions that have opposing behaviors, which really means that you have one direction along which you have a local maximum, another direction along which you have a local minimum, and that forces the presence of a saddle point. Okay, not that we needed to know that, but it's good to have some understanding of what is hidden behind such a mysterious statement. It is a mysterious statement, and it's not quite transparent as to why we need something like that, or as to why something like that actually works. But let's do a second example. So I'm looking at this from an old problem set. I hope the numbers work out fine. We'll find out, I guess, but here's the example. So find and classify the critical points of the function f of xy is equal to y cubed x plus 12y squared minus 8x. So again, let's begin by finding the critical point. So what is the partial derivative with respect to x? It's going to be y cubed minus 8. And what is the partial derivative with respect to y? It's going to be 3y squared x plus 24y. Now, you see how this works very nicely for us. If we set these two equal to 0 in order to come up with these equations right here, then you see that the first equation is easily solvable. What do we get from this one? We get that y is equal to 2. Once we know that y is equal to 2, we can plug it into the first one, and that will give us 12x plus 48 is equal to 0. And that will imply that x is equal to -4. So that tells you that there is just one critical point, and that's the point -4, 2. So that's all we need to classify for this function. And we need now the second order partial derivative. So f(x) is 0. Fxy is 3y squared, and fyy is 6yx plus 24. Okay, so let's find the determinant, which will be f(x) at -4, 2, fxy at -4, 2, fxy at -4, 2, and fyy at -4, 2. How much are these quantities? So this one is going to be 0, and fxy at -4, 2, I'm looking at this right here. That will be 12. So I have another 12 down here. It doesn't really matter what fyy is. I mean, I can find it since in the computation it's multiplied by 0. But let's find it. So it's going to be 12 -48 plus, I think it's -24. Like I said, it doesn't matter, because what we find here is -144, and this is less than 0. And obviously what we have is a Pringle point. Okay, I called it saddle before, let me call it Pringle. And that's all the classification that needed to be done in this case, where we were quite lucky to have just one critical point. So, for example, this function on its whole domain of definition doesn't have a single local extremum. Hence, it doesn't have any global extrema. So you see how nicely we can draw a conclusion on global extrema. Actually, if we went back to the example that we did before, and we asked, can we answer the question of whether we have a global extremum for this function? So we have one local minimum. Can we say that this is a global minimum? And obviously the answer here is going to be no, because this function can have arbitrarily large negative outputs. So this function doesn't have any global extrema either on its full domain of definition. And that does it. Thank you for watching.